Among statisticians, by far the most common measure of dispersion is not the range or the interquartile range or anything like that. It is the variance and its very close sibling, the standard deviation. Those two statistics, along with the mean, do all of the heavy lifting and almost all of statistics. And they're not terribly intuitive, extremely powerful, but they just don't make sense to students at first. It requires a lot of thought and a lot of practice before you start developing an intuition. I'm going to try my hardest to actually walk you through why the formula is what it is. I don't want to just start with the formula. I could put it down and it would look scary and you'd stop listening. So instead, what I want to do is take our time and work through a couple of different versions, kind of building our way up. We'll start with an intuitive description of what we might like for something like a variance. We'll see that it falls short in a couple of different ways. We'll consider ways to fix that formula, and we'll do that iteratively, and after a little bit of work, we'll arrive at the final formula. I think this is a better approach than just memorizing, because when you just memorize, you don't really understand. And so you usually tend to forget that kind of stuff. So let's do this. What does variance mean? All right, we want a measure of dispersion. Now think about a nice bell-shaped curve. We've got our histogram, right? We got our distribution of values. And we got our middle point here, and that turns out, since it's nice and symmetric, that's our average. We've got some spread, right? We've got a high value, we've got a low value, we've got that range. But consider that the range of values, like the variance in values, to use that word, is different here with this high and this low than if we had something like this. We'll take the same high and the same low and the same average, but what about this distribution? The first line and the second line have the same range. They have the same high and the same low. But I'm pretty certain, like if I knew something came out of this second red distribution, I know that like almost all those values are practically going to happen in a very well-defined region. Whereas with this first blue line, man, those blue values could take on a whole bunch of different values. It could be pretty high, it could be pretty low, close to the max, close to the min. They're not nearly as well defined as this red second line is. So I'd like to develop some measure of dispersion that can differentiate between these two distributions. I think one way of thinking about it is that the distance of these second points to their mean is very small. That gap is quite small for most numbers. Whereas the gap for the blue numbers, if I can switch colors, that gap is much bigger. Right, so for these blue numbers, for a lot of numbers, that gap between their value and the mean is pretty big in both directions there, whereas it's very small for the smaller numbers. So maybe a measure of dispersion should be how far each number is from the mean or the average. So let's make up some numbers. Let's say we got some data on X. I don't know, we have a 60, 80, and 100. So just three numbers. What's the average? Well, we can do that pretty quickly. The average We'll call that x bar. The average is 60 plus 80 plus 100 divided by 3. Hopefully you can see that that number is 80. All right, so what about dispersion? And we said that I think an intuitive description of dispersion should be how far each number is from the mean. So each of these three numbers is how far away from the mean. All right, so let's do x minus x bar. That would tell us the difference of 60 from 80, 80 from 80, and 100 from 80. So this distance right here is 60 minus 80. That's negative 20. Here it's 80 minus 80, or 0. And then here it is 100 minus 80, or a positive 20. Okay, so I can see that that observations tend to be either 20 above the average or 20 below the average, or exactly equal to the average. I've got a bunch of numbers here. I'd like to have one statistic that kind of summarizes all of these distances, all of these differences. Well, the obvious one for me is just to take the average of these numbers. So let's modify our intuitive definition here. Let's modify this definition so that we can kind of collapse these into one number. So let's add a couple of words there. So I don't just want to calculate three different numbers, how far each number is from the mean. I want to know how far each number is from the mean on average. So I need to calculate the average of these three numbers. So what's the average of 20, 0, and negative 20? I hope you can tell that it's 0, right? Just take 20 plus 0 minus 20 divided by 3. That's got to be 0. So shoot. Does it sound like it sounds like I have no dispersion, and clearly I do. I went from 60 to 100. Is it just because I had data that was nice and symmetric? Right? There was no huge outliers. This number could have been 100,000 with a bunch of zeros, and then would I have gotten a 0? Well, let's try a few more examples and see if that's the case. It's going to be easier for us to do that with Excel. So let's switch over to there real quick. Okay, so I have Excel. Let's key in some data for X. We said we had 60, 80, and 100. And let's just line up all these. Let's center those values. Then we had our mean. Let's call that X bar. And this was just the average of all of these numbers. So that's A2 through A4. But let's just go even further. It's not going to affect anything. Missing values don't even count against us. And yeah, our average was 80. So let's copy this formula down. But I'd like for it to, when I copy it, like notice, I want just 80s. What happened here was that my formula updated when I copied it down, and now it's just saying a 3 all the way down. So I'd like to anchor this number here. So I'm going to put a $sign in front of the A and a $sign in front of the 2. While I'm at it, I may as well do it in front of the other numbers as well. Those $signs mean that I don't want to update that formula in that place whenever I copy the formula down. So I still get my 80, but now when I copy it down, I get 80s again. Okay, now I want to do X minus X bar. So that's just A2 minus this number. We get our negative 20. Let's copy our formula down. Just grab that small little square right there. You can see the mouse kind of changes shape when you hover over that, and then you can copy formulas all the way down. And we wanted to calculate the average of these numbers. So let me just highlight them, and then look to the bottom right here, and we can see that the average is 0. In fact, yeah, let's do it right here. The average of C2 all the way through, in fact, let's anchor this guy, C2 all the way through to C20. That average was 0. Okay, so all I've done so far is just replicate what we did by hand. Let's start changing numbers and see what happens. So rather than having 100, let's have it be 100,000. Now, of course, the average changes. And so the distance from the average changes. But the average value didn't change. The average value is still 0. Right? Highlight these numbers. Check down here. Yeah, 0. Well, what if I had more than 3 numbers? Maybe it's just a function of having 3 numbers. Let's key in a bunch of other numbers. All right, let's take our formulas and copy those down so that they update. No, look at that. My average is still 0. I mean, I have new numbers, which means I have new averages, which means I have new distances from average. But when I average these numbers, I get 0 again. So I'm starting to get convinced here that, well, the average distance of each point from the average is 0. And when you say it that way, it kind of makes sense. Each point is different from its average, on average by 0, because the average is right in the middle. So I'm going to have like some numbers that are above average, some numbers that are below average. On average, they balance out. This is like our deer hunter example. He got some people undershooting, some people overshooting, so on average, we got them. So, well, that's good because it helps us make sense of the joke, but it doesn't help our bigger purpose of coming up with a good measure of dispersion. Let's go back to our slides and keep thinking about what went wrong and how we can fix it. So we just said how far each number is from the average on average. Well, we just figured out using Excel, and we can actually do a mathematical proof of this. That's fodder for a different video. But we just figured out something. We just figured out that how far each number is from the average on average, that is always equal to 0. So no matter whether I'm using the blue line or the red line, this formula that I thought made sense gives me the same number. It's always 0, which means it's just not informative at all. So what happened? Well, what happened here was I had a 20, but it was exactly offset by a negative 20. So the problem is that I had negative numbers. Really, what I want is the distance of each number from the mean. So maybe I should have done like absolute values. And in fact, some statisticians do that. They say, listen, rather than just x minus x bar, what we should have done is x minus x bar absolute value. All right, so negative 20 then becomes a positive 20. 0 stays at 0. And positive 20 stays at positive 20. And now how far each number is really is a positive distance. The average of this is 20 plus 0 plus 20 divided by 3. What's that number? What's 40 divided by 3? I don't know. Let's do that real quick. 40 divided by 3, 13.33. Okay, So if this guy here, this average was 0, this guy was 13.3, 3 repeating. We can use this. So it's still the average distance from the mean, just we make sure that it's a positive distance. Now I got to tell you, and I know this is disappointing, that this isn't the formula that statisticians actually use. We use something a little bit seemingly more complicated. It achieves the same ends, and it turns out it's better in a whole slew of different ways. Our problem was the negative numbers. Now, what's another way of getting rid of negative numbers? Rather than just taking absolute value, we could square these numbers. So take x minus x bar, but don't take the absolute value. Now just square these numbers. That'll get rid of negatives. So negative 20 times negative 20 becomes a positive 400. 0 squared is 0, and positive 20 times positive 20 becomes positive 400. Now what's the average of this? 266, I think. Let's see here. We got, what was it? 400? 400 plus 0 plus 400 divided by 3. Yeah, 266. All right, so that 266.66 repeating, this is the formula that statisticians actually use. And so it's not how far each number is from the mean, or in other words, it's not the distance of each point from the mean on average. It is now the squared distance, or the squared average distance of each point from the average. That is, in words, what statisticians mean when they say variance. So let's clean up our slide and actually put out a formula, and then we'll talk about some deficiencies in even this formula and why we might want to make one last tweak and make it into a standard deviation. So let me clean up my slides. Okay, so variance. Variance, we said, is the squared distance of each point from the mean on average. All right, so take any one particular point, calculate its difference from the mean. We call that x bar. Don't stop there. We want the squared difference. And we want to do that not just for one particular value. We want to do it for all values. So do it for all values there with that subscript I. And then add up all of those. There should be some number of them. We'll call that number n. And then we said we want it on average. So how do you calculate an average? Add up a bunch of things and then divide by the number of things. That's our variance. You'll often see it denoted, at least in my class, variance of x, v of x. In some statistics textbooks, you'll see it with a Greek letter sigma squared and a subscript x, which is kind of obnoxious, but it's also ubiquitous. It's in every stats textbook, and so you should at least have seen it. I'll try to just do v of x or var of x because it sounds like variance. All right, so that's our formula. It's the squared difference of each value from x on average. So we got to add them up and divide by n. But our number, like still can't understand that in an intuitive sense. When we calculated this thing, the average squared distance of each point from the mean was 266. Well, where did 266 come from? We had three numbers in our data set. We had 60, 80, and 100. The range there was 40 units. It went from 60 to 100. What is 266? 266 what? If these are points on an exam, then what are the units here? 266 what? Points? There's no 266 points. Well, actually, turns out it's 266 squared points. Who the heck thinks in terms of squared points? I want to know what I got on my score. I want to know, like, did I do better than my classmates? I don't want anyone to tell me, well, the square of your points was blah, blah, blah. Like, it's nonsense. Squared points. Or if this was dollars and this was like $60,000 worth of family income, $80,000 and $100,000 worth of family income. And I said, well, how dispersed are all these household incomes? What's the income distribution like in the United States if these three numbers represent that? And you're going to turn around and say, well, 266,000 square dollars. It doesn't make any sense. So on the one hand, we had this nice intuitive formula that we came up with, and yet the output of that formula is pretty not intuitive. Squared dollars or squared points. The squared business is what's screwing us up. We need to get rid of that square term. Now, some people say, good. The problem started here. We should have just stayed with absolute value. That would be too simple. It's not what the statisticians did for other actually very important reasons. But what they did was they said, listen, the problem is sure enough in that squared term. Let me change colors again. The problem is in that squared term. So you get like squared dollars or squared points. So how about this? How do you undo squaring something? You take the square root. So that's their solution to kind of bring this back down into units that we can understand. Is they said, listen, take your variance number, take your formula, and how about you just take the square root of that guy? We'll call that the standard deviation. I like to call it STDev of x. Statisticians kind of run with this guy. They said, well, listen, if the variance is sigma squared subscript x, then the standard deviation is just the square root, right? Because we're taking the square root. And so the square root of sigma squared just becomes sigma. And so that's how the statisticians arrive at the standard deviation. They just call it sigma because variance is the square of that. It's sigma squared. You'll see that everywhere as well, so you should at least be aware of it. I'll try to avoid that as much as I can and just stick with var x rather than sigma squared, or STDev of x rather than sigma. Some of it is going to be unavoidable.